Okay, good morning everybody. I know you may not have finished your feedback forms yet, but you will have some more time later. Okay, so this is the last of the lecture style presentations for this course. We will have a tutorial to follow. What I'm doing here is I've picked out one complex natural product, and we're going to look at one synthesis in detail and one in a little bit less detail, which means there'll be lots of reactions there, but I want to point out the ones that are related to the organometallics reactions that I was talking about yesterday. So the natural products are a whole group of natural products. Here is one of them. They're the Manzamine natural products. So you can see very complex, lots of rings here with a bridge across the top, a carbazole moiety up here, and so on. So this was isolated. It's a marine natural product. It was isolated in 1986. Has promising profiles against the Leishmania parasite. It has this very unusual structure. Some work on imitating the proposed biosynthesis of this compound was undertaken by Baldwin at Oxford in the late 20th century. But if you want to think about something like this for proper biological evaluation, there is very little material available from the natural source, from the sponge, and it's environmentally unsound to be collecting tons of sponge to isolate natural product. So that's where the drive to synthesize this molecule came from. The wish to investigate the biology and the fact that it's an unusual looking structure. So there are some references there. This is Stephen Martin from Texas. And so we'll look at what he was proposing. Here are some other alkaloids of the same family. So you can see some of them have the same type of structure, some of them are a little bit simpler. And you can see how if you have a route to this kind of system, you should be able to make variations and of course make some compounds that are not natural products. So let's start with the retrosynthesis. Excuse me. So you can think about taking this molecule apart to take off the aromatic heterocycle at the top, so that you're really spending most of your efforts in putting together this complex ring system. So that was the idea, was to think about taking this carbon out of the heterocycle here as an aldehyde. So in the forward direction, that would correspond to what's known as the Pictet-Spengler cyclization. You could imagine that this ring here, it's an unusual ring size, but that should be very possible via a ring closing metathesis. If you imagine taking that apart, then you need alkene here and alkene here to do the metathesis. At the same time, you might need to have this aldehyde protected until you're ready to do the final heterocycle closure. There is another alkene in a large ring here, this bridging chain. So you could imagine putting that together by a ring closing metathesis as well. That would mean this chain on the left and this chain on the right would form the bridge across the top of the molecule. At the same time, consider taking this amide bond apart And here you have effectively something that is protecting this alcohol and this amine together as a cyclic carbamate. This group over on the right-hand side could be put in by an alkylation reaction of some sort. What are we doing here? Can't quite see what the change is there. If you consider going back a bit further, it might be more convenient for this aldehyde oxidation level actually to be a carboxylate, be a little bit more robust. Thinking here of maybe this amine position here, that ring closure might be done if it was an amide, and then of course in the forward direction you'd have to reduce that carbonyl group out. And these alkenes that you're going to need for part of for the two different ring closing metatheses, you might want to build those by Wittig reaction chain extension, and the aldehydes that you would need to do that might have come from alcohols, and there they are protected. So this is still analyzing it backwards. You could imagine making the six-membered ring here via a Diels-Alder cycloaddition, and if you take it apart in that way, you get the structure shown in the bottom left here. How are you going to make the diene for that? Well, perhaps you could assemble that via a Stille coupling, which would mean you'd need a bromo alkene here and the corresponding ethenyl tin derivative. That leaves you with a simpler looking compound, especially if you take apart this amide bond, because then you have a smaller heterocycle, which could be this. You have a long chain here, which would be this part, and then you have the tryptamine, you have the heterocyclic bit ready to go in at the very end. So it comes back to three manageable pieces, and then of course you have to assemble those and then put everything together with all the functional group transformations that makes. So that's quite a complex analysis, but hopefully you can see how from this rather tricky looking structure at the top, how you can bring that back via relatively sensible steps, but depending on a Stille reaction and two ring closing metatheses, back to three components that don't look too bad. That makes the synthesis, of course, also quite convergent, because you've got three relatively equal sized pieces which you're going to bring together later. Now, tryptamine down here, you don't have to make that. That's commercially available. So what you do have to make are these other two pieces. So this shows how they are made. This amino alcohol protect the nitrogen, protect the oxygen as a silyl derivative, tertiary butyl diphenyl silyl chloride. Doesn't really matter what group, just for the purposes of this lecture, but just to think it's a silyl protecting group. Then the protecting group is taken off the nitrogen. That was there just so that you got selectivity between nitrogen and oxygen, and then a Michael addition, a conjugate addition of the amine to this unsaturated aldehyde. Chain extend this carbonyl group, this aldehyde, by a Wittig reaction, and you can see now it didn't really take too long to put together this piece. I'm not quite sure what's happening in that step. Doesn't look like anything's happening. Okay. The nitrogen ring compound on the bottom here can be made from a commercially available derivative of the carboxylic acid, aspartic acid, and reduction of the ester group, protection of the alcohol with a silyl protecting group again, and then protection of the nitrogen with the tertiary butyl oxycarbonyl function gives you this. And that's ready to put in this carboxylic side chain using a strong base, lithium hexamethyl disilazane, to form an enolate at this position, react that with carbon dioxide to make the carboxylate, then sodium borohydride to reduce this carbonyl of the amide. You might think that's a very mild way of reducing amides, but it's actually an imide because you have a carbonyl the other side of the nitrogen. This is the more reactive carbonyl. In fact, it's more ketone-like than normal, so you can do it with sodium borohydride. And then sodium carbonate to make sure you have the sodium salt of this carboxylate, because from this reaction it would have been the lithium salt. Those two are then joined together. The oxalyl chloride to make the acid chloride here, and then an amide formation with this secondary amine. And then comes the creating the diene for a Diels-Alder reaction via a Stille coupling of this bromoalkene with ethenyl tributyl tin, vinyl tributyl tin in a non-systematic nomenclature. A palladium 0 catalyst, reasonable looking conditions there, toluene reflux for 30 hours. That's making the diene here by making the middle bond of the diene, and then clearly under those thermal conditions the Diels-Alder reaction actually takes place. So you're adding 2 carbons and closing the 6-membered ring all in one go. So here are, if you like, 2 reactions that we've looked at this week, the Stille coupling and the Diels-Alder reaction actually being used in the same transformation. That gives this compound. It's now beginning to look a little bit more like what we want. Now we've now got to build in that we need an oxygen functionality and an alkene chain on this side for metathesis, and we need to make some more alkenes for metathesis on the left-hand side as well. So that structure, this is the same as was on the last step of the last slide. There is an allylic oxidation to put in the oxygen function, oxygen atom you need here. There are various ways you can imagine doing that. I don't know why they chose this one particularly, chromium trioxide in pyrazole. But anyway, all that's doing is oxidizing this more sensitive position next to the double bond to make this carbonyl derivative. The protecting groups are removed from these 2 oxygens at the same time as each other under acidic conditions, and then Swern oxidations to take the primary alcohols to aldehydes. And then Wittig reaction happens on each of those aldehydes to put in alkenes, and this is trying to set the stage for what are going to be metathesis reactions later on. This ester group was there to help with the Diels-Alder reaction and to be more robust through the sequence. We actually want that as an aldehyde oxidation level, eventually to join on the heterocyclic bit that's going to go on the top there. So ester to aldehyde is done by dibal, which in this case is actually going not down to the aldehyde but down to the alcohol, which is then oxidized back with the so-called Des-Martin reagent. But overall transformation here is ester to primary alcohol to back to aldehyde. It's easy, it seems crazy to over-reduce, but actually it's easier to do that than to try and stop this reduction. You might think I could do that with dibal at very low temperature, but very often you get a little bit of over-reduction, so you might as well go all the way down and then oxidize back up. The aldehyde here is protected as a dimethyl acetal. Now, the third of the alkenes you need for the ring closing metathesis is put in now by a lithium alkyl derivative. That adds to the carbonyl group over here to give, that would give an alcohol, but the alcohol you get from that reacts with the carbonyl group in the tertiary butyl oxycarbonyl to displace tertiary butoxide, and that effectively is the oxygen protects itself by forming this cyclic carbamate with what this carbonyl here is coming from the Bock group. So it's now becoming more and more like the intermediates proposed in the retrosynthesis. We now have an alkenyl chain here and an alkenyl chain here, and this can build the bridging large ring across the top. G1 means Grubb's first generation catalyst, done in dichloromethane at reflux, so that's not too high a temperature, in 3 hours, and it gives an 8-to-1 mixture of the Z to E. So the Z double bond that you need there, the cis double bond, is the favoured one, and that's presumably due to the constraints of the conformation of that large ring. Remember I said that metathesis tends to give the thermodynamic ratio of products. So that's presumably what's happening here. And in quite decent yield, 67%. So again, we're getting closer and closer. We've now got to build an 8-membered ring around the bottom here. So there's the molecule that was on the last slide again. We'll build in the other side chain. It's got to be attached to this nitrogen, but that nitrogen is currently protected, so base hydrolysis to remove this carbamate protection, that leaves alcohol here and an amine free here that you can then acylate with a long chain acid chloride. That puts in enough carbons to react with the vinyl group that's already there to make the 8-membered ring. Once again, Grubb's first generation catalyst worked here, but you'll notice quite a lot of it was used. You might argue that that becomes, at 110%, that becomes a reagent rather than a catalyst. But if you look at the probability factor in the previous slide. Look at the... In the previous slide. Yeah, the middle one, the two alkenes are at the two ends of a molecule. Yeah, but you need this bridge to be on the top face, and actually this is relatively flexible here. There's quite a lot of conformational flexibility here, and this is already up on the top face. So it looks like, and when you draw it, it looks like it's far apart, because you're trying not to draw the atoms on top of one another, but actually the probability, it is flexible enough for those two to meet. I think this is one of the remarkable things about metathesis, that it can do things like this, which look on paper a bit crazy. This perhaps looks a little bit less crazy, but for whatever reason, it's obviously not very reactive metathesis here. Maybe it's the strain in an 8-membered ring, whereas the bridge across the top is a much longer chain, a little bit more flexible. Here, you're going to get totally this cis double bond, because you can't fit a trans one into that ring size. That was followed by an acidic workup, which is just to remove the protecting group from the aldehyde at the very top. Because now you're ready to, everything is now ready. This is essentially the full bottom half of one of the natural products. You don't need that carbonyl group though. That was there just to bring in the side chain to do the metathesis, but you don't need it. So that amide is reduced. Not surprisingly, it reduces the aldehyde at the same time. You might argue that it would have been better to keep the protection for another step. But I guess they tried that and found that it worked just as well this way round, because the aldehyde's reduced again and is oxidized back to the the aldehyde's reduced again to the primary alcohol and then is oxidized back to the aldehyde. There is another point of this though, that is that at this stage in these sequences you perhaps don't have very much material, so you can't necessarily, when you're trying to reduce this, you can't necessarily go back and think, well, maybe I shouldn't have taken that protection off, because you may not have the material there. So this may have been a pragmatic decision rather than the best strategy. But then once you...
With the reduction of that for carbonyl of amide after 9 yes. Then there will be OH reduction.
Yes, it'll reduce to carbinol, but then the nitrogen will eliminate the oxygen, and then you'll get an imine bond which will then further reduce. So that's how amides are generally reduced, via the carbinol.
DNDL dimer that's made in imine
Is, sorry?
And with which reagent you have do the reduction of imine?
Oh, dibal is going the whole way through, but the first thing it does is it adds to it reduces the carbonyl to an OH, yes. Then the nitrogen in the same reaction, or in equilibrium, pushes out the OH. Actually, it won't be OH, it'll be O-. It pushes out as an oxygen, as an aluminium alkoxide. That gives a double bond N here, which is reduced again by the dibal. And then the final condensation is between this aldehyde and this tryptamine, and you form a bond to the nitrogen. You form an imine bond with the nitrogen, and the imine carbon is then attacked by the indole double bond acting as a nucleophile. The bits I wanted to focus on were the Stille reaction to set up the Diels order that made this 6-membered ring here and here, and then the 2-ring closing metatheses, which are the difficult bits because they're the larger rings. The rest is, if you like, fiddling around with the functionality to make sure that you get the right reactivities later on. It's a long sequence, admittedly. It's 21 steps, the longest linear sequence. The overall yield, if you calculate it based on things you can get out of the bottle, is 0.19%. But that's almost inevitable with a synthesis of this length and complexity. But it shows, I think, interestingly, a standard heterocyclic condensation to make that, and we'll see a difference to that in a moment with another synthesis of this molecule. It uses a Diels order reaction to make that cyclohexene, and it uses ring closing metathesis, and it had used a Stille coupling to make, if you like, those two carbons, half of the diene, and it's used ring closing metathesis to make these two rather unusual rings. Before metathesis was developed and properly systematized by people like Grubbs and Schrock, it would have been very difficult to imagine how you would put those two rings together. So those to me are the key features of this. Well, I guess the key feature really are the two metatheses, and then along the way you've also used the Stille and a Diels order reaction. Now, of course, no one expects you to remember all of this, but what I'm hoping you can see is how you can work through this. You design in these more complex reactions, the metathesis and the Diels order and so on, and then you make everything else work so that you can use those reactions that are going to set up the difficult pieces. In particular here, the two rather large rings. So that was a synthesis from Stephen Martin in Texas. This is a synthesis from a friend of mine, Darren Dixon, at University of Oxford, which is a little bit more recent. It's a slightly different approach. I'm not going to go through this in as much detail, but there are some differences, and it still uses some of the reactions that we've been looking at during this week. So a lot of this says the same thing, basically that you need to do the synthesis to make more material because you can't get enough to do proper biological evaluations from the natural source. And of course the syntheses should allow some variation by putting in different groups at different times of some to make some analogues of the natural materials, in other words some non-natural analogues. Now some of this analysis is the same, but here's a different one. In the Martin synthesis, the carbon that's going to end up in this pyridine-like ring was built in as part of the bottom piece. In the Dixon synthesis, that bond is cut apart in a Stille reaction. It does a ring closing metathesis to make this long bridge, because probably you can't imagine another simple way of doing that. And then some further disconnections to take it back and so on. So this is the group you would need, or that or a halogen there, to do the Stille reaction. That could have come from a carbonyl, as the derivative of the enol of a carbonyl group there, which here you're sort of imagining the protection of it. If this top bridge is going to be from a ring closing metathesis, let's take off all the bits of that. Here's one half of it. Here's where the other half would be added in. That's similar to the Martin synthesis. And then this ring is disconnected because I didn't want to do a Diels order reaction. I was looking this morning to try and work out exactly how they closed this six-membered ring, but I didn't quite have time to find that paper in the Journal of American Chemical Society website. So you can take this back without going into as much detail this time to some smaller components. As I say, I'm not going to look at as much detail in this synthesis as the other one. Really, one thing I want to point out is making this compound, doesn't look so different to the one that Martin made. Only this time, Dixon made the 8-membered ring before the big long bridge. That 8-membered ring did come from a metathesis, but I'm not going to describe that. Then the next part shows very similar in a way to what Martin did. He used a lithium derivative here. This time it's a Grignard reagent to bring in the right-hand side chain alkene. There it is. Now, there isn't a joint protection between the nitrogen and oxygen here in this case because the nitrogen is already part of the 8-membered ring. So here this is set up to ready for the metathesis, but they made the enol derivative, triflate derivative of the enol, before doing the ring closing metathesis. That also illustrates that the ring closing metathesis conditions are quite mild in the sense of groups other than alkenes remaining unaffected during those reactions. So this again used the Grubb's first generation catalyst, in this case 20 mole%, so that's still higher than some catalyst proportions that you see used, but it's not as much as the 100 mole% that was used in one of the metatheses in the Martin synthesis. But I want to illustrate here, again, Grubb's first generation, relatively mild conditions. It'll be heat, it'll be reflux dichloromethane. Again, a Z to E ratio, not quite as favorable to the cis or Z compound as in the other synthesis, but in a decent yield. So that's illustrating another example of the ring closing metathesis. And here's the Stille reaction. There's a typo here. This should be a halide on the left hand side here, because this is just meant, it looks like nothing's happened there, but this is meant to show a halopyridine derivative being turned into the tin derivative ready for the Stille coupling. Potassium hydride, which protects the nitrogen as an anion effectively, then tertiary butyl lithium, which does a lithium halogen exchange on what should be drawn as a halogen in this structure. I didn't draw these, but I didn't notice the mistake until this morning. And then the lithium derivative on the pyridine is reactive with tributyl tin chloride to make the tin derivative you need for a Stille coupling. So on the previous slide we put together this structure, having just closed the very big ring across the top of the molecule, and then the Stille coupling just takes the full heterocycle that you've just made as a tin derivative and reacts it with this double bond with effectively a leaving group on it. Could have been a halide, but in this case it was done using the enol ester derivative, and you get a Stille coupling. Not the best yield in the world, but not bad, considering the complexity of this bottom piece. So again, this synthesis has used a ring closing metathesis to make the large ring. It actually used one to make the 8 ring, although I haven't shown it on the slides, and then it's got a Stille coupling to put the two key pieces together of the final molecule. If you do the Stille coupling under slightly different conditions and instead of using the heterocycle, you use carbon monoxide, then you make a molecule that is also a natural product, ursinal A. So this triflate intermediate effectively therefore has some flexibility in that you can use it to put other things on the top, on that top of the molecule. If you do the coupling with, in the presence of carbon monoxide and methanol, you can actually get that to go through the palladium acyl derivative reacts that you get with the carbon monoxide, then reacts with methanol, so you can go, rather than going to the aldehyde with just carbon monoxide, you can go through to the ester with carbon monoxide followed by methanol to react with the palladium acyl derivative. So that's another, this is the methyl ester of natural product, which the natural product was the acid. So using that same intermediate, you're getting out two natural products and the ester of a third natural product. And I think that's the last slide. So that's all I want to say there, but I wanted to go through that example because the two syntheses there just picked, not quite at random, but picked out to show how some of the organometallic couplings and the metatheses, and in the first case a pericyclic Diels-Alder reaction, are useful things in complex synthesis in the last few years. I could have found some others, I just happened to pick that natural product out. Now, before we take a break, I also wanted to go back to something we did yesterday where I couldn't understand what was going on in the slide. It's this one at the bottom here which was confusing me, and it did say mechanism there, and sure enough, yes, you need to think about that. What's going on there? And I did a bit of investigating overnight, well, yesterday evening, I suppose, to work out what was going on. First of all, I checked out these, and this is the perils of using a slide that you borrow from somebody else. First of all, I checked out these two references. They're nothing to do with this reaction, as it turns out. They are to do with the synthesis of this natural product, but they're to do with the synthesis by a different strategy. Then when I eventually looked up other work on this frondosine natural product, I found a reference from 2011 which actually did have this reaction in, but then I discovered that that was drawn wrongly, and these in the reaction as shown here, which is meant to be illustrative of gold in complex and with an alkyne, actually these O-methyl groups are still O-methyl groups in that product. As somebody pointed out yesterday, they've changed. Well, they shouldn't have. That's been, when this has been drawn out, that was a mistake, so it should still be 2-methoxys here. Nevertheless, it's still a rather weird reaction. I couldn't quite see what was going on. So then I went back to the predecessor of this paper where the gold type reaction was discovered, and so I'm going to show you what I found out about that one, I hope. If I can just find the right things. Now, when this strange reaction of gold with the alkyne and then apparent rearrangement, well, it is a rearrangement, was discovered. It wasn't discovered on those, it wasn't first reported on that natural product synthetic route that we were looking at. So, but I got this scheme out of a paper from some Japanese authors, and I just put this in to illustrate what's going on. So we have an alkyne and an acyl group, in this case an acetoxy. It was a pivalloyl in the other example, and we'll see how that relates in a moment. And yes, you are still getting gold complexing to the alkyne and giving electrophilic activation. The nucleophile that's adding to the alkyne is the neighbouring group, so it's a neighbouring group participation. That was the bit that I hadn't realised till I saw this. So forget all the rest of this stuff, this is a different example. But so we've got an acyl group here, an ester attached to, on the next door position to an alkyne, gold complexes, that activates the alkyne towards nucleophilic addition. What's the nucleophile? It's participation by the neighbouring acyl group oxygen. You can draw the product of that, there should be another curly arrow in there, as an oxonium ion, and it's captured it. Then the bit that I didn't realise until I saw this was overall this acyl group ends up migrating because the other, so one CO bond is formed to the alkyne, it can only reach the near end of the alkyne, so that's where you form this 5-membered intermediate. And then the other CO bond, the one that originally joined the acyl group up here as well, is broken by electrons pushing through from the gold, and what you end up with is a gold carbene, and you end up with the acyl group, in this case an acetoxy, having moved. It was on the group attached, in this case you can tell it's moved because it was on the same carbon as the phenyl, half of it's on the same carbon as the phenyl, and overall it's moved, and there is a gold carbene attached to a metal, so it's a carbenoid. What can carbenes do? Well, this was something from earlier in the week. They can add to double bonds to make cyclopropanes. In this case, it's the double bond of the furan. In the case of the natural product we looked at yesterday, it's a double bond that was in the that was branching off the cyclohexene. So we get this 1-2 migration, and then we get a cyclopropane formed on where there was a gold carbene. So after the migration, you would have a gold carbene at this position. That reacts with an added alkene to form a cyclopropane, and the gold that's around just is complex to the alkene that's left. Now if the alkene that you add is actually part of a diene, then you've got one of the double bonds here, and you've got another double bond in the side chain. And that's of interest because that then is set up to do a cope rearrangement. 1, 2, 3, 4, and then a double bond 5, 6. So that's where the 7-membered ring in the example that was on yesterday's slide, that's where it comes from. So gold activates the alkyne, that helps the 1-2 migration of the acyl group to take place, leaves a gold carbene on the remote end of what was the alkyne. That adds to another alkene to form a cyclopropane. If that cyclopropane, or at least if that alkene you add, has another double bond in it, like here, then you can get a cope rearrangement to form a new 7-membered ring. And that's actually what was happening in the example that was on the slide I showed yesterday. So it does all make sense, and the reference that should have been there is this one at the bottom here. It was subsequent to the references that were supposed to be making that natural product. It's actually from 2011. So alkyne activation, acyl migration, leaves a gold carbene, does a cyclopropanation. If that leaves another double bond hanging off, then you can get a cope rearrangement to give you a 7-membered ring. And if I go back to wherever it was, that's how this 7-membered ring arises. It is then, that would actually leave a derivative here that is then hydrolyzed or methanolized to give this carbonyl group. So this is the acyl group that migrates, 1, 2. Here is to give a gold carbene. That's the double bond that adds to the gold carbene. That leaves, and that's the extra double bond that then takes part in the cope rearrangement. So it does all make sense. It's just that there's an error here in that the methoxys are still on the ring, and there's an error there in terms of the fact it was the wrong references. It's the same natural product, but it was later than this. This was an earlier synthesis, and then the other one was added later. So I just wanted to show you that first of all apologize for the errors in the reference and the errors in the structure here, and secondly to show you how that reaction really does fit into what I was saying about gold activating alkynes and then nucleophiles adding, but in that case it went on a bit further and actually did 2 other reactions that we've talked about this week: carbenes in cyclopropanation and cope rearrangements. Okay, so that's enough for this first session. So if we take a break and then we come back in half an hour or so, and then we'll have another tutorial, so one of the open sort of problem sessions. Okay.